A single egg, 5 grams of calcium, protein, and biological precision. And yet, this delicate capsule must endure what no machine of its size ever could. Thousands of kilometers, sudden thermal shocks, vibration cycles, handling by humans and robots, and all without losing its internal equilibrium. Each year, more than 1.2 billion eggs cross borders, climates, and altitudes to feed cities around the world. They travel inside containers, trucks, and planes, not because they are strong, but because someone, somewhere, has calculated exactly how not to break them. At first glance, an eggshell seems like nature's most fragile invention, but under axial compression, pressure applied evenly from top to bottom, it's a marvel of structural integrity. Engineers know this shape: the arch, the dome, the load, distributing geometry that holds cathedrals and bridges together. The eggshell can withstand impressive vertical loads, but twist it slightly or let it resonate under vibration, and it fails in silence, cracking not from a blow, but from fatigue, just like a turbine blade or a rail wheel misaligned by half a degree. In fact, the analogy isn't poetic, it's mechanical. Think of the seed metering discs used in precision agriculture. Their job: rotate and place each seed without damaging it. Misalign the angle, and the disc shears the seed's protective coat, compromising germination. Now compare that to a pallet of eggs in motion, a rotation off-axis during shipment, maybe due to a curve, a slope, or a misaligned loading ramp, can compromise hundreds of shells. Not visibly, not instantly, but structurally. The damage begins microscopically and worsens with every bounce. Heavy industry understands this. Freight rail operators use phase-matching protocols to prevent vibration harmonics that would otherwise destroy steel coils in transit. These systems synchronize wheel, axle, and cargo behavior like a mechanical symphony. Yet in egg transport, we still use basic suspensions, foam padding, and plastic trays, hoping rather than calculating that they'll suffice. We shield the outside, but ignore the vibration profile inside. We focus on what breaks, not on what's about to break. There's an even more overlooked danger: cumulative microfractures. Tiny structural compromises in the shell that develop from repeated stress. Invisible, untraceable, until the final handling causes a cascade of breakage. These fractures aren't random. They follow patterns of road quality, of vehicle suspension, of tray geometry, and yet few shippers track them. There is no fracture log, no stress model, only loss reports at the warehouse. So here's a question worth asking. If we model vibration to protect industrial cargo worth millions, why don't we do the same to move a 5-gram, calcium-bound biomechanical capsule filled with nutrients and life? Why do we design containers for weight and not for resonance? Each egg is more than food. It's a precision object, and every time it travels, it exposes the hidden limits of our logistics and the untapped potential of agricultural engineering. Eggs don't usually break in front of us. They break inside closed trucks, inside sealed containers, in the space between a vibration and a curve. And when they arrive fractured, we often assume the issue was speed or impact or human error. But the truth lies deeper, in a frequency mismatch between the suspension of the transport vehicle and the geometric configuration of the egg trays themselves. When both systems resonate at the same frequency, they amplify one another. The result: thousands of invisible fractures triggered not by force, but by oscillatory resonance. This is not speculation, it's mechanical reality. This understanding is reshaping how eggs are protected. Engineers working in agricultural logistics are now looking beyond foam and rigid plastics. One of the most promising innovations is the use of triaxial, shock-absorbing trays, capable of absorbing vertical, lateral, and longitudinal forces simultaneously. These trays borrow from orthopedic injury prevention materials, using phase-shifted silicone dampeners that behave like cartilage under pressure. The system doesn't just absorb shock, it delays and diffuses it, redistributing stress in all directions. It's a kind of biomechanical interface between egg and infrastructure, Still, many carriers believe that slowing down is the safest solution, but data contradicts this intuition. On urban delivery routes in Latin America, eggs transported at 38 kilometers per hour suffered a 12% higher structural failure rate than those moving at 48 kilometers per hour through smooth logistics corridors. The variable isn't speed, it's continuity. Inconsistent road surfaces generate unpredictable vibrations, while stable corridors allow the load to travel with harmonic integrity. The myth that slower is safer is being dismantled by real-world telemetry and fracture mapping, and some companies are acting on this. One exporter in Mexico retrofitted their crates with modular dampening grids, inspired by scaffolding systems used in earthquake-resistant buildings. By introducing geometric flexibility into the crates themselves, not just their supports, they reduced shell loss by 22% in a single fiscal quarter. This wasn't about cushioning, it was about dynamic stress reallocation, the same principle used in aerospace packaging and high-performance electronics logistics. So here's the insight we must carry forward. Egg protection isn't about foam, speed, or caution. It's about understanding the resonance threshold specific to each route, each road curvature, each suspension system. It's about replacing static defense with dynamic tolerance engineering, because the fractures that matter most aren't visible. They're silent, cumulative, and entirely predictable. If we know where to listen, temperature is not a number, it's a process. And in the world of egg logistics, maintaining that process is more than just keeping things cold. The egg is a living capsule, even post-lay, with an internal environment that reacts to temperature cycles in ways that standard refrigeration cannot always control. Most systems measure shell temperature. You understand what's happening inside, because inside, the albumin, the egg white, behaves like a biological fluid under stress. It thickens and thins with thermal variation. It shifts, it separates, it destabilizes. And when it does, it silently displaces the yolk, alters internal pH, and changes the entire biochemical structure of the egg, long before the shell ever cracks. The damage doesn't come from heat alone. It comes from the recooling cycles. Every time a cooling system temporarily fails and restarts, it creates a thermal swing. These swings push the internal mass into motion, not enough to see, but enough to deform. Eggs with perfect shells arrive downgraded, their contents unstable, unsellable, and standard logistics protocols never detect the moment it happened. That's why a new generation of transport technology is redefining cold chain management. At the heart of it, thermal inertia, modules using phase change materials, or PCMs. These materials don't cool or heat, they buffer. They absorb excess temperature during spikes and release it slowly, smoothing out fluctuations without consuming energy. It's a passive system, but engineered with molecular precision. The egg doesn't experience the swing because the PCM absorbs the shock. This is not insulation, it's thermal modulation. The difference is measurable. In controlled experiments, containers equipped with PCM panels maintained ideal albumin density for up to 40% longer than traditional systems under the same conditions, including short power failures. That extra time can be the difference between a Grade A and a Grade B shipment, between full sale and partial loss. One logistics hub in Germany took this concept further. They implemented multi-phase buffering systems during the peak of a summer heat wave. By modeling thermal drift over long-haul routes and deploying layered PCMs tuned to different phase thresholds, they preserved product integrity with surgical precision. Their outcome, a 19% reduction in downgrades and a complete redefinition of how egg viability is evaluated. The lesson here isn't about chilling harder, it's about chilling smarter. We can no longer afford to calibrate cooling based on outer shell readings alone. What matters is the yolk-centered thermal inertia curve, a model that maps how the inner mass responds hour by hour, kilometer by kilometer, because the egg is not passive cargo, it is a biomechanical system in thermal flux. And the future of egg logistics lies in engineering for that invisible complexity. Before we move on, think about this. We engineer climate control for 5 grams of albumin, but how often do we apply that same precision to the choices we make? There's something curated for minds like yours. Check the pinned comment. It's not just relevant, it's made with the same attention to detail as everything we've shown so far. Behind every crate of eggs that arrives intact at a supermarket, there's a sequence of calibrated decisions, mechanical, thermal, logistical, that mirrors the complexity of any industrial system. And yet, for decades, egg logistics has relied on legacy methods. Fixed-size trays, rigid routing, temperature goals based on shell touch. But now, as agricultural engineering evolves, we're seeing a transformation. A shift from static handling to adaptive systems, systems that think, that react, that treat the egg not as a passive object, but as a sensitive biomechanical unit in need of tailored support. In modern seeding equipment, smart drills automatically adjust their impact force based on seed size, shell resistance, and moisture sensitivity. Every grain, every capsule is treated with nuance. The same principle is now being applied to egg transport. Shell density varies between breeds. Shell fragility increases with the laying hen's age. Albumin thickness decreases the longer the egg remains in storage. These are not trivial factors, they are engineering variables, and for the first time, logistics systems are beginning to account for them in real time. One of the most sophisticated examples comes from the Netherlands. The company Ovolegix has developed an egg crate that isn't just a container. It's a smart structure, equipped with vibration feedback sensors and real-time egg weight deviation tracking. It can detect stress accumulation across the load. If one section begins to register excess fatigue, even if no cracks have formed, the system can reroute the shipment in transit. Not metaphorically, literally. The truck's route is dynamically adjusted based on live biomechanical readings from the eggs themselves. This isn't science fiction. It's a redefinition of what agricultural logistics can be. An egg is not just something to protect. It's something to monitor, to understand, to engineer around. With these systems in place, protocols become more than rules. They become biomechanical adaptation frameworks, responding in real time to the needs of the cargo. And perhaps this is the most revealing comparison of all. We design combine harvesters with programmable calibration for 10-gram wheat kernels. Every vibration, every cutting angle is calculated. Yet we continue to transport 50-gram biological capsules, rich in water, protein, gas exchange, and internal pressure, using century-old cartons and static routes. Agricultural logistics is not just about moving products. It's about respecting their complexity, recognizing that food is not just cargo. It's the result of natural architecture, human ingenuity, and mechanical discipline. The egg, small as it may be, deserves a system that treats it with the same precision we give to machines. Because in the silence of the cold chain, what's truly moving is more than just shells. It's a testament to how far our intelligence can go when we finally decide to listen to the engineering inside the ordinary. Every egg that survives its journey is more than proof of good packaging. It's a micro-victory of physics over chance, of intelligence over inertia. In the vast and often invisible machinery of global food distribution, eggs are among the most deceptively simple objects. But they reveal something essential about the way we engineer the systems that feed us. The shell may look fragile, the load may seem light, but the logistics are anything but. When we follow the egg from hatchery to container, from truck to shelf, we uncover a chain of decisions that reflects the sophistication of today's agromechanical thinking. We see tray geometries modeled on seismic architecture, suspension systems adapted from orthopedics, thermal modules using materials once confined to aerospace and pharmaceuticals. Each of these interventions comes not from tradition, but from technical respect for a living material that does not forgive poor handling. And maybe that's the larger lesson. Agriculture is no longer just about producing food, It's about understanding how food behaves in transit, how it responds to vibration, temperature, acceleration, time. Just as we once learned to tune harvesters for terrain and seed, we are now learning to tune containers, routes, and cooling for each item's internal dynamics. Logistics is no longer passive. It's adaptive. It's sensitive. It's smart. In this shift, the egg becomes a symbol of everything modern agribusiness must protect and understand. It is no longer enough to transport without loss. The challenge now is to engineer for resilience before failure, to model what cannot be seen, and to listen to what the cargo silently reveals. Because in the end, agriculture is not only about feeding people, it's about designing systems that respect the biological architecture of what feeds us. And in doing so, it reminds us, behind every intact shell lies a story of geometry, temperature, material science, and human insight applied with precision. The world is moved not just by machines, but by the quiet engineering of the fragile. Before you go, take a second to check the pinned comment.